made space and leading to the galaxies we see at night. We'll learn about how stars are born and die, what makes our solar system work, and even the chances of finding life somewhere else in space. Join us as we uncover the secrets of the universe, how it affects us here on Earth, and what might happen in the future. The Big Bang Theory is the leading explanation for the origin of our universe. Imagine the universe as an immensely dense and hot point, roughly the size of a grain of sand. This point contained all the energy and matter that would eventually form everything we see today. Around 13 billion years ago, this tiny speck began to expand rapidly, an event we now refer to as the Big Bang. This expansion wasn't just an explosion in space, rather, it was the expansion of space itself. In those first moments, temperatures soared to unimaginable heights, and as the universe expanded, it cooled down. This cooling allowed quarks and electrons to form. When conditions became favorable, these quarks combined to create protons and neutrons, forming the building blocks of atoms. Over millions of years, clouds of hydrogen and helium, the simplest elements created during this period, began to coalesce under gravity's influence, leading to the formation of stars and galaxies. The light we see today from distant galaxies can be traced back to this primordial event, giving us a glimpse into the universe's early moments. The Big Bang Theory also accounts for the observed abundance of these light elements and the cosmic background radiation that fills the universe, an afterglow from that early moment. This radiation serves as a snapshot of the infant universe, revealing information about its composition, temperature, and expansion. In this way, the Big Bang Theory not only explains how the universe began, but it also opens a window into the fundamental processes that continue to shape it today. The theory of cosmic inflation emerged from the need to explain certain puzzling aspects of the universe's early development. Scientists recognized that the observable universe is remarkably uniform. This means that despite vast distances between galaxies, the cosmic microwave background radiation, a remnant from a hot, dense state shortly after the Big Bang, is evenly distributed. However, this uniformity raises a question. How could regions so far apart be so similar if they had never been in contact? To address this conundrum, cosmologists proposed that an incredibly rapid expansion, or inflation, occurred just after the Big Bang. This expansion would have stretched those small, uniform regions across vast distances in a fraction of a second, smoothing out variations and creating the homogeneity we observe. Supporting evidence for inflation comes primarily from observations of the cosmic microwave background itself. Measurements from satellite missions, such as the Wilkinson Microwave Anisotropy Probe, have revealed slight temperature fluctuations in this radiation. These tiny deviations in temperature point to the quantum fluctuations in density that would have existed before inflation, which were then stretched to cosmic scales during that brief period of rapid expansion. Additionally, the large-scale structure of the universe, including how galaxies are distributed in clusters and voids, aligns well with predictions made by inflation theories. It suggests that these structures formed from the small initial inhomogeneities forged during the inflationary epoch. Finally, studying gravitational waves, ripples in space-time that are generally produced by immense cosmic events, has provided another potential layer of evidence. If inflation generated gravitational waves as theorized, future observations could validate the inflationary model even further.